And welcome to today's session. So we will be continuing ahead with heat transfer today. Yeah, good afternoon, everyone. And we will look at, we'll be starting with the last portion of heat and thermodynamics, that is heat transfer today. So we will start with heat conduction, which is a very interesting and also important topic from your JEE point of view. And there are certain things in which heat transfer becomes kind of analogous to electric current transfer or electric charge transfer or current electricity, and thereby we'll be learning some things which will be useful for us later in our study of current electricity also through the study of heat transfer. So let's begin. You must also be doing questions from heat and thermodynamics, the first law applications in heat engines, etc. So yeah, I will be keeping some time aside for discussion of the module in these coming few lectures. So today's lecture also, in the second half of the lecture, I will keep some time aside in the end for discussion of the doubts, particularly from the module. Yes, Kevin, you can send me the doubts and questions that you have. We will discuss them. Okay. You can just send me the question numbers if you have from the module, or if you have from some other source, you can just send me a message on WhatsApp with the question. I will discuss those particular doubts. Okay. Let's start with the discussion of heat transfer today then. So as all of you are aware, there are three primary modes of heat transfer: conduction, convection, and radiation. So from our discussions about heat and thermodynamics in general till now, we understand heat as a form of molecular kinetic energy, and we understand temperature as a measure of the average molecular kinetic energy of matter. So absolute temperature or temperature measured in Kelvin is directly proportional to the average molecular kinetic energy, be that the vibrational kinetic energy of solids or the rotational, translational, or vibrational kinetic energy of gas molecules or liquid molecules. That is, together we can club them as fluid molecules. So whether we are talking about fluid molecules that are basically moving about in random motion, or we are talking about solid molecules which can only vibrate about their mean positions. But all molecules possess kinetic energy, which is what we collectively call the heat energy or the internal energy by virtue of heat of a given material. And therefore, that internal molecular kinetic energy, or what we call heat, always tends to transfer, or in common language, we'll say heat flows from a region of higher temperature to a region of lower temperature. And that process by which the heat flow occurs or the transfer of heat occurs, that is studied in this particular section of heat transfer. So we say that there are three, I mean, experimentally observed, we can say that there are three primary modes of heat transfer, and they are referred to as conduction, convection, and radiation. So these are the different modes of heat transfer. As you know, in among these solid materials, primarily experience heat transfer by conduction, whereas fluids, inclusive of liquids and gases, primarily experience heat transfer through them by virtue of the mode of convection, whereas radiation is something that is by independent of medium. Radiation is a mode of heat transfer that can happen independent of the medium through which heat is transferring. Radiation is therefore the primary mode of heat transfer through vacuum. Okay, so it is independent of any medium, or you can say any material medium. Okay, so in fact, radiation is that form of heat transfer where the heat energy is transferring by photon energy or electromagnetic energy, and therefore not through kinetic energy of molecules of materials. Yes, that's also true, Somaru, but over here, the primary three modes of heat transfer that we'll study is conduction, convection, and radiation. Okay, and then there is, at more sort of elaborate kind of level, there are some further sub branches of heat transfer. That is where the concept of advection comes in. Okay, but primarily at the basic level, these are the three classifications of the modes of heat transfer. So let's start by understanding conduction today. So conduction is the mode of heat transfer for solid materials where heat transfers from one region in a solid material to another region in a solid material by the transfer of vibrational kinetic energy of molecules. Okay, so this is the primary mode of heat transfer in solids. Okay, via the transfer of molecular vibrational kinetic energy. Okay, from a region of higher temperature to a region of lower temperature. Okay, or in better language, we can say that heat transfers from, or you can say heat transfers across temperature gradient. Across a temperature gradient through the transfer of vibrational kinetic energy from molecule to molecule. And thereby it becomes the primary mode of heat transfer in solids. Okay. Now, if at the experimental level we want to understand the properties of heat conduction and the mathematical relations with the rate of transfer of heat via conduction with respect to other physical parameters like the temperature gradient or the physical properties of the particular material, the solid material through which heat is transferring, and also its geometrical dimensions, etc. Then we can start by understanding experimental results from a very basic type of situation where we are looking at heat transferring along one dimension, that is along one axis, in what is called an isotropic material or a homogeneous material. Okay? So first of all, we study the most basic type of heat conduction where heat conduction is happening in one dimension, okay, or along a straight axis, okay, along a homogeneous or isotropic. Isotropic basically means homogeneous as far as physical properties are concerned. So any material is called isotropic when its physical properties are homogeneous over its substance. So across along a homogeneous or isotropic solid material. And such a material is called a heat conductor because it is conducting heat. So any solid material is a heat conductor, but some are good conductors of heat and some are poor conductors of heat, depending on their physical properties. So a good example of a study of such a material, experimentally speaking, would be heat conduction along the axis of a metallic cylinder, solid, isotropic, and of uniform cross-sectional area. Okay. So just imagine you have a solid metallic cylinder and we are studying its properties with relation to heat conducting across its own axis or across its symmetry axis, you can say. So to set up an experiment like this, what we will have to do is first of all, we will have to insulate the solid cylinder on its curved surface so that heat cannot escape along the curved surface, and heat only transfers or conducts along its length. So the metallic cylinder will have to be wrapped around with some kind of perfectly insulating material or some kind of poor conductor of heat in comparison to metal, so that none of the heat that is transferred to it from some other heat source is going to radiate or convect out from the surface, and the heat only conducts along its length. Okay. So this is our solid metallic cylinder. And to understand the physical properties of this process of heat conduction, we will have to create some insulation, some heat insulation on its outside surface, so that the heat is only going to transfer along its length and it's not going to transfer across its cross-sectional area and escape from its surface. So that's one part of the arrangement. And the other thing is that we will have to keep the two ends of the rod consistently at a temperature difference. So we will have to create what is called a constant temperature reservoir of two different temperatures at each end, so that each end of the rod is maintained at a constant temperature, but individually different temperatures. So hope you're understanding what I mean by this. So these are constant temperature reservoirs, so that the two ends of the rod are maintained at uniform temperatures. But one of them will act like a heat source at higher temperature T1, let's say, and the other one will act like a heat sink at a lower temperature T2. So T1 is greater than T2. Okay. Also, this solid cylinder has a cross-sectional area of capital A and a length of L. So once we've set up this experiment, if we have some way of measuring how much heat is transferring or how much heat is conducting across the rod from the higher temperature end or from the heat source end to the lower temperature end, with respect to time, what is the rate at which heat is transferring? Then from that, we can understand the physical properties of the process of heat conduction. So that is what this experiment is all about. Okay. Just think of it from an experimental point of view, that we are setting up this experiment and we have some way of measuring the rate of heat conduction. That is the number of joules per second that are conducting from the heat source to the heat sink through the length of the metallic rod. And we can also control various different parameters, like we can control the values of T1, T2. We can adjust the length of the rod if required. We can adjust the area of cross section. We can do the experiment with different metal rods like copper and silver, etc., to study the difference in their properties individually compared to each other with respect to heat conduction. So we can create all these variations in the experiment to understand the physical parameters of heat conduction, how they affect each other. Okay, so this is our experimental setup to try and understand more about heat conduction. All right, I'm just going to scroll up for a minute so that we can just go through these points. Then we'll start discussing what are the observations from such an experiment. If we were to actually conduct the experiment, what is it that we would observe? Okay, so let's see the expected observations from such an experiment. So an example of a heat source could be we could continuously pass steam here at 100 degrees C. And as the steam is condensing into water because of heat transfer, we keep removing the water and keep supplying a fresh amount of steam. We keep passing at a certain rate a fresh amount of steam and removing the water which condenses. So thereby this end will be maintained at 100 degrees C. So T1 is maintained at 100 degrees C. It's a constant temperature reservoir. And same way at the other end, we could pack ice at 0 degrees C. And as the incoming heat by conduction melts some of the ice, we remove the water form and keep stocking up fresh amount of ice, packing it with a fresh amount of ice so that it remains at 0 degrees C. So ice at 0 degrees C. So this is one practical method at the laboratory level to maintain this constant temperature heat reservoirs. Okay, that we have some kind of a process going on at each of them for the heat sink and the heat source, which will make sure that the temperature remains constant, independent of how much heat is coming in or going out. So that kind of a process typically is a state change process, because you know that during state change, the heat transfer doesn't result in temperature change. It results only in state change. So as the steam is condensing at one end, as long as we keep supplying fresh amount of steam and removing the condensed water, we will not be allowing the temperature of the steam of that end to be coming below 0 degrees C. Similarly, as we keep the other end packed with ice, as long as we have a fresh stock of ice as the ice melts, and we maintain a certain amount of ice at 0 degrees C, we'll be able to maintain the temperature at 0 degrees C continuously. Okay? So that's how we practically achieve this purpose of having constant temperature reservoir. Okay. So having done that, what we will observe from such an experiment, let's understand. Okay. So the observation will be that initially, okay, the conductors, or in this case, the metal rod, the conductor or metal rod undergoes a state of what we say flux, that is rapidly changing temperature. At different points. Okay, so it's undergoing a state of flux. It's not in a uniform state, or it's not in a steady state. Okay, and different points on it. So if we are doing the experiment and while we are maintaining these two ends at temperature T1 and T2, okay, if we have some mechanism by which we can actually measure the temperature at various different points. So I have, some thermometers attached here, here. At 5 or 6 different places, I have thermometers attached. So all of them will be showing a rapid change in temperature. So I have, for example, I have 5 thermometers, okay, to monitor temperature at different points. So what we will observe is that initially, okay, all 5 would have been indicating room temperature. That is, Ta is equal to Tb is equal to Tc is equal to Td equal to Te is equal to room temperature of 300 Kelvin or 27 degrees C or something like that. Okay. But now what happens? But when the two ends of the rod are subjected to constant temperature T1 and T2. In my example, T1 is 100 degrees C and T2 is 0 degrees C. Now we will see that probably A, B and C will show a rapid temperature rise. Okay. And probably D and E will show rapid temperature drop. Not that flux. Okay, that is electrostatic flux or magnetic flux. This term flux just refers to a state of change. Okay, not to be confused with electrostatic flux or magnetic flux. Those are different things. Okay, they are related with fields. That is related to electric field or magnetic field. So you can imagine this, the moment you place this rod in this situation, that one end is maintained at 100 degrees C and the other end is forcefully maintained at 0 degrees C. So some part of the rod, it will start cooling down rapidly. Some part of the rod, it will start heating up. And eventually, okay, but with time, with sufficient time, okay, while T1 and T2 are maintained at constant temperature, okay, the temperatures of every other points also stabilize. So what we mean by this stabilize is that they become constant with respect to time. Okay. So for example, it may so happen that the temperature of the thermometer here that I've attached, it might stabilize to 90 degrees C. The temperature of this other one might stabilize to 75 degrees C. The temperature at C might stabilize to 50 degrees C. The temperature at D might stabilize to, let's say, 20 degrees C. The temperature at E might stabilize to 5 degrees C. Okay. Just I'm saying, for example, it depends on where, depending on where the thermometers are placed. Depending on the exact position of the thermometers. Okay, okay. Kevin, I'll do that. Okay. So more importantly, let's understand this. So what's happening now? Initially, before I had put the put the rod in that situation where it is between the two constant temperature reservoirs of T1 and T2, it would have been at room temperature. So the whole rod would have been at a uniform temperature of 27 degrees C. So wherever I place a thermometer on the rod, it would have read the same room temperature of 27 degrees C. Okay. But now I subject it to that special condition that I am forcefully maintaining one end of it at temperature T1 and the other end of it at temperature T2. So when I just about start this process, that I put the rod between the two reservoirs, I will see that the rod is in a state of thermodynamic flux. That is, the temperature is rapidly changing. Like if you have kept thermometers stuck to those different points, you will literally see the values of temperature changing very fast with time because the rod is undergoing a huge thermodynamic change. But with time progressing, you will see gradually the temperature start to stabilize. The rate at which the thermometers are changing value will start to decrease, and eventually they will become constant with respect to time. So it's not that the thermometers are showing the same value. All five are showing different values, but their individual values have stabilized. They are not changing anymore with respect to time. And depending on where I have placed them, so I'm saying, for example, I might have placed A closest to this end. So it's showing a temperature of 90 degrees C or 95 degrees C or something like that. It stabilizes at a comparatively large temperature compared to the other four. Then the next one I've placed is TB. The next one I've placed is C and like that. So they will all show a decreasing temperature as you're going from A to E because you're going from the hot end at T1 to the cold end at T2. So they will all show stable values, but a range of values. All right, better. So this point is clear, na, Kevin? The difference between steady state and the state of thermodynamic flux. Okay, so when the rod reaches this state where the temperatures of at different points have stabilized to constant values. Okay, so there's a difference between saying constant and uniform. It's not uniform because TA is not equal to TB, TB is not equal to TC. They're all different values of temperature because the thermometers are at different locations. But the values are not changing in time. They are constant with respect to time. So that's what we mean by saying that the temperatures have stabilized. They become constant with respect to time. So when that happens, we say by definition, the rod has reached steady state. Okay. So this is the condition for steady state. Okay. So this is the steady state for the given heat conductor, in this case, the metallic rod. The moment the temperatures have stabilized at different points on the rod, we say that it has reached steady state. Okay. And now we will understand the mathematical relations to the different physical parameters at steady state. So at steady state, first of all, the rate of heat conduction is uniform in the rod or conductor. How we can say that? Okay, I'll explain in a moment. So it means the same rate of heat conduction in joules per second or watts. Okay. So the same rate of heat conduction, which we will call delta Q by delta T in joules per second or watts, is taking place across the rod or through a cross section at any point in the rod. So whether we've chosen a cross section at the point A or B or C or D or any other point on the rod, the rate at which heat is flowing through that cross section is going to be the same in joules per second. And that rate of heat conduction is generally what we write as delta Q by delta T. Amount of heat flowing per second. You can also understand it as dq by dt, but generally for whatever reason in this type of thermodynamics, we use the term delta q by delta t instead of instantaneous dq by dt. So basically they mean the same thing because it's become uniform. Okay, so let's understand why this is happening in the first place. This is occurring in the first place because now for the conductor, of course, you maintain the two ends at temperatures T1 and T2. So the end points of my rod are maintained at this constant temperature T1 and T2. But in steady state, the temperature at every other point has also become constant. So this end is at T1, this end is at T2. But if I take any arbitrary point P here, it is at some temperature T. So at steady state, the temperature T is constant. It's obviously less than T1 and greater than T2. Okay. So that means if I now consider an imaginary thin cylinder or thin section of the rod. So for this imaginary thin section of the rod of length dl, what is happening? The rate of heat coming in from this side must be equal to the rate of heat going out from this side. Okay. Because it's in thermal equilibrium, its temperature is not changing. Okay. But I know the temperature at this end of the rod is more, so heat must be coming in from this side. I know the temperature at this end of the rod is less, so heat must be going out from this. But at the same time, the temperature of this small section is not changing. So at steady state, this temperature is constant. That means incoming heat must be equal to outgoing heat. Okay, in any time interval, delta t. So that's why delta q by delta t is uniform at all points. Okay, because from cross section to cross section, heat is flowing now. Flowing across. So whatever heat is coming from this cross section to this cross section must be balanced by this, must be balanced by this. So at every point, the same rate of heat transfer must be happening, or the same rate of conduction must be happening. Very much like electrical current. Okay, because no point in a conductor starts to accumulate electrons or starts to accumulate positive charge. Every point in the conductor remains neutral. So the incoming electric current at any particular cross section must be equal to the outgoing electric current. So there's a uniform electric current passing through the entire conductor. So like that, there's a uniform heat current, or there's a uniform rate of heat conduction, delta Q by delta T at all points. Yes, of course. Yeah. Because here we are assuming that heat is flowing. That's correct, Aman. We are assuming that heat is flowing only along the length of the conductor. Heat is not escaping from its surfaces. So we have set that up by insulating the outside. So that is very important over here. And also the material of the conductor is isotropic. It's not like, for example, it's not like an alloy which has different percentage of mixture of the different metals at different points. Because then the conduction properties will be different at different points. Okay, so we have facilitated that in our experiment, that heat is flowing along a one-dimensional axis, because we've insulated this from outside. So all that is very necessary. Okay. Also, the area of cross section is uniform everywhere. It's not like the rod is thicker somewhere and thinner somewhere else. All right. So once we have established that there is a uniform heat current or rate of heat flow, next what we can see is what this depends on, this actual rate, how it is. So this will be directly proportional to the temperature difference, directly proportional to the area of cross section, inversely proportional to the length. Okay. So for a conductor, in this case a rod of cross sectional area A, length L, with its ends maintained at constant temperature, T1 and T2, T1 greater than T2, delta Q by delta T becomes the uniform rate of heat conduction through its length. And this is a constant rate. It's not only uniform at every point, but it's also a constant rate. So that's why delta Q by delta T is equal to dQ by dt. As long as we are maintaining the two ends at constant temperature T1 and T2. So not only this is uniform throughout every point in the rod, but it's also constant with respect to time. If we are maintaining this temperature T1 and T2 over a very long period of time, so at any point of time in between, the rate of heat conduction through the rod, as long as the rod has reached steady state, will be the same. It will be delta Q by delta T, which is proportional to the temperature difference and inversely proportional to the length of the rod and directly proportional to the cross-sectional area. Okay. Now the constant of proportionality here is a physical constant because obviously delta Q by delta T is in watts. Temperature difference is in kelvins. Area is in meter square and length is in meter. Okay. So that particular constant K, it is called the thermal conductivity and it is a material property of the rod. This is the thermal conductivity of the material of the rod. Okay. It is expressed in watts per meter Kelvin or joules per meter second Kelvin. Just for example, the thermal conductivity of copper is about 385 watts per meter Kelvin, whereas the thermal conductivity of aluminium is a poorer conductor, so it's approximately about 205 watts per meter Kelvin. Okay. These are experimentally determined. Similarly, brass is something closer to 100, much poorer conductor of heat. Whereas if you take thermal conductivity of a poor conductor of heat like wood or something, comparatively poor, it's much less. It's about 0.17 watts per meter Kelvin. Thermal conductivity of air is very poor in comparison. It's 0.00 something. You don't need to remember these values. I'm just giving you an idea. Glass is also comparatively poor thermal conductor compared to metals. Concrete is also very poor in thermal conductivity. Yes, that's correct. Tungsten is a very good conductor. Oh, Aman, lightning is a different thing altogether. Lightning creates electrical conduction. So the heat generation in during electrical conduction is huge. Okay. But for example, if you have an air gap between two concrete walls, it creates good insulation from heat transfer. You're understanding the point? Lightning is a different proposition altogether because lightning occurs because of extreme electric field that is generated when clouds carrying different amount of charge uh, when they collide with each other. So it is the effect of charge actually, charge conduction and not heat conduction. Heat conduction, heat generated is a byproduct of the extreme amount of electrical current that flows through during lightning. So that's the physics of lightning. Yes, that's true because of the electrical conduction during lightning. Anyhow, so this is about thermal conduction. Okay. Now the final aspect about steady state, which is also very important. So for an isotropic conductor in steady state, the temperature gradient is uniform. And there's a very easy way to understand why this happens, or in a sense, you can say to understand a sort of proof of this. So if we maintain our heat conductor with the two ends at constant temperatures T1 and T2, such that it's in steady state, so there is a uniform rate of heat conduction happening through it. So we know that this delta Q by delta T, or you can also write it as dq by dt, instantaneous rate is equal to average rate of change. So that is Ka by L into T1 minus T2. Now this is a uniform rate of heat conduction at all points now. This is the uniform, what we call heat current. Okay. So now within this, if we consider a small cross section, or we consider a small section of the rod, which is of length delta x, okay, as opposed to the entire rod, which is of length L. Okay. Now this end of it is at T. So this end will be at T plus delta T. Okay. So now through this, the same amount of heat transfer is happening. Okay. So this delta Q by delta T is equal to this, because there's a uniform heat current. So this heat current must be equal to this heat current. The rate at which heat is transferring at any other point is equal to the rate at which heat is transferring through that small section of the rod of thickness delta x. So now comparing these two equations, you can see that delta T by delta x is equal to T1 minus T2 by L. So that shows that there is a uniform temperature gradient, delta T by delta x. So if we are to visualize the relationship between temperature and position inside the rod, this would show us that the temperature at any point, which is let's say over here, that a distance of x from this end. So the temperature at any point P would be like this. Like this. because the temperature in terms of position in steady state would be a graph having a uniform gradient, or that means a uniform slope. So if at x equal to 0, the temperature is at T1, and at x equal to L, the temperature is at the value T2, then at any other point in between, you can just see it from the slope. Some general point x. You can see that T1 minus T2 by L is equal to T1 minus Tp by x. Uniform gradient, or that is delta T by delta x. So the temperature difference between any 2 points divided by the distance between those 2 points along the axis is what we call the temperature gradient. Remember, we discussed about gradient before also in mechanics. Gradient is rate of change with respect to position. So here we are talking about temperature gradient. That means change in temperature or rate of change of temperature with respect to position, delta T by delta x. So that is uniform, and its value is equal to T1 minus T2 by L, as long as the material we are dealing with is an isotropic material. Yeah, this equation and this equation are the same, these two. I'll just explain to you, Aman. This is the same as this. Okay, like we can show that T1 minus T2 by L is equal to T1 minus TP by X. So that will give us this relation. Okay. On the other hand, we can also show that T1 minus T2 by L is equal to temperature at the point P minus T2, but divided by the distance between them is L minus X. We are comparing now this point with this point. So that will give us this equation. Okay, like that. So let's understand a numerical example to figure out all these things. So now we are doing exactly the kind of experiment we were discussing about earlier. So between two heat constant temperature reservoirs, we are having a heat conductor. Okay. And everything else we have kept insulated. So this is a metallic rod of length 5 meters, cross-sectional area 20 centimeters square, and thermal conductivity of the metal is, let us say, 250 watts per meter Kelvin. Okay. Now here we are continuously passing steam at 100 degrees C. This is all insulation. Okay. Whereas here we have packed this chamber with ice at 0 degrees C. So given the latent heat of ice is 80 calories per gram, and take 1 calorie as 4.2 joules. At steady state, find the ice in grams melted per minute due to conduction. And second, find the temperature of a point at distance x from this steam end of the rod.
So can you scroll up for a bit?
So you just arbitrarily take any point inside, which is at a distance x from this side. You want to find the temperature at that point at steady state. Okay. So you'll see that we can do this question quite easily by just applying the principles that we've discussed above. That at steady state, two important things. The rate of heat conduction, delta Q by delta T, is given by this formula. Okay. And again at steady state, that temperature gradient is uniform and given by this formula. Okay. So this is all you need to use in any such numerical problem, nothing else. It's very simple application. It's very simple, at least at this stage where we are dealing with isotropic materials with uniform cross section and all that. Once we move on to non-isotropic materials where K is variable and all that, a little bit more complication will come in, or area of cross section might be variable. So we have to use calculus, integration. Okay. But here it's a simple unitary method kind of application. It's quite easy. So just try this out, people. Okay, so how many grams of ice are melting per second? I'm getting different answers from different people, so I'll just verify the answer for you. So see, at delta Q by delta T at steady state, the so-called heat current or rate of heat conduction is given by this. So this will become 250 into, now area of cross section was what, 10 centimeters square or 20 centimeters square. So we'll have to convert that.
Yes.
So 20 into 10 raised by minus 4 in meters square divided by the length, which was 5 meters, correct? Okay. And this was watts per meter Kelvin. So that's all right. Into the temperature difference, which is 100 in Kelvin. So this will give us delta Q by delta T, the whole thing, in watts or joule per second. So delta Q by delta T will come out to be 10. Okay. So this is how much now? Into, so 10 raised power 3 into 10 raised power minus 4. So that's 10 raised power minus 1 into 2. So that's 10 raised power 1. Is correct?
Yes.
Yes, sir.
Okay.
Yes.
10 joules per second. Okay. So therefore, in 1 minute, delta Q will be 600 joules, or
Yes.
600 divided by 4.2 calories. Okay. So the mass of ice melted per minute will just become this delta Q divided by L. So 600 upon 4.2 into 80. So whatever this is now.
1.7.
1.8.
Yeah, how much is this coming to? 1 point something.
1.78.
Okay. So that will be in grams per minute, right?
Yes.
Yeah, nearly 1.8 or 1.79 grams per minute. In fact, you can think of this like a delta M by delta T, because it is grams per minute. Okay, good. So that's done. Now for the second part, we just have to use the formula for temperature gradient, right? Second part, you can just think of it like just making a graph, no? So across 5 meters, our temperature is dropping by 100 degrees C. So per meter, it is dropping by 20 degrees C. So we plot in degrees C. So you can see that at 4 meters, it would have dropped to 80 degrees C. At 2.5. So obviously the midpoint. So it's very obvious that this will be exactly half. So it will be 50 degrees C. And at 4, it should be 20 degrees C. Because the slope of this line is delta T by delta X is minus 20 degrees C per meter. Or you can even say it is minus 0.2 degrees C per centimeter. Okay, so very simple direct application, nothing difficult about these type of questions. Okay, so next up we look at combination of conductors. So before that, what we can do is we can compare heat conduction with electric conduction or conduction of electricity. So when we subject this to temperature T1 and T2 with insulation and all that, we can say that the heat current delta Q by delta T into the temperature difference. Okay. And like that, when we have an electrical conductor which we subject to a potential difference. So this point is at potential V1, this point is at potential V2. Then there is electric current which is delta small q by delta T, rate of flow of charge. That is potential difference divided by electrical resistance. This is our Ohm's law. Okay. Where resistance is rho L by A or L upon sigma A, where sigma is conductivity, electrical conductivity. Electrical conductivity. Okay. So comparing these two equations, we can see that it's a perfectly analogous situation. Okay. Heat current can be thought of as temperature difference divided by something called thermal resistance, where that thermal resistance is L upon Ka. Whereas electrical current is potential difference divided by electrical resistance, where electrical resistance is L upon sigma A. So this is electric current potential difference and electrical resistance. And analogous to that, here we have heat current in watts, whereas electrical current was in amperes. We have temperature difference and we have thermal resistance. Okay, now generally speaking, good electrical conductors are also good thermal conductors because the good conductivity comes from free electron availability, which also creates good thermal conductivity because the free electrons can conduct heat through their vibrational kinetic energy also very efficiently, just like they can conduct electricity because they are free from the nuclei. Okay, so for example, now suppose we have situation like this. Where we have two different metallic rods, that is, they're made of different materials, but having the same cross section. And they are subjected to temperatures T1 and T2. And there is some insulation from the outside. So two metallic rods in series combination. L1 is equal to, let's say, 6 meters. K1 is equal to 300 watts per meter Kelvin. And L2 is equal to, let us say, 4 meters. And K2 is, let's say, 240 watts per meter Kelvin. And they have a common cross-sectional area of 10 centimeters square. T1 is equal to, let's say, 200 degrees C, and T2 is minus 40 degrees C. So we have to find the net rate of heat conduction and also the temperature of the junction. Find delta Q, delta T net through the combination. And the temperature of the junction between the two rods, both of these at steady state. Okay, so for anything like this, you can just use the convenience of your previous knowledge of electrical circuits and just convert this into a circuit problem. As you can see, they are in series combination. Okay, Kevin, that's correct. Very good. Okay, you can send me any doubts that you have from the module, Kevin, from first law of thermodynamics. After discussing this question, we will discuss some doubts. Okay. Okay, so let's just convert this into a sort of heat circuit type of problem. So this is R1. This temperature of the junction is, let's say, T. This is R2. And this is T1, this is T2. So this is equivalent to a single resistor of R1 plus R2. So these two will be equivalent in terms of current. So R1 is L1 upon K1A and R2 is L2 upon K2A. So these will become 6 upon 300 into 10 raised by minus 3. So that is 1000 by 50 or 100 by 2 or 50 and 4 upon 240, 10 raised by minus 3. So that's 1000 by 60. So 100 by 6 or 50 by 3. So it is 20. Okay, so R equivalent. So the heat current. Now, as far as the temperature of the junction is concerned, this temperature, you can see that yes, you can use either of these formulae, but I prefer this. Okay, so make sure you check the answers for this. Yeah, Kevin, I'll scroll up. Okay, so if this question is clear to all of you, I'll come to some of your doubts from heat and thermodynamics. So first of all, there are a couple of doubts in chapter exercise number 4. So I'm coming to that. Okay, let's look at these two questions. This is in chapter exercise 4 of heat and thermodynamics module 3. So work done by 1 mole of a gas to increase its temperature by 12 degrees C at constant pressure is. So work done in isobaric process is P delta V is NR delta T. So there should be 1 mole of the gas to increase its temperature by 12. So this should be close to 100, I think. That should be nearly 100 joules. So 99.8 joules to be precise.
So in the answer key, it is given none.
Oh,
Yes.
Okay. So just make a correction. It's nearly 100 joules. Okay. Change in internal energy to increase the temperature of 10 moles of an ideal gas by 30 degrees C. Adiabatic constant is 1.5. So if gamma is equal to 1.5, okay, what can we say about the degrees of freedom or the value of Cp, Cv, etc.? So Cv we can directly write as R upon gamma minus 1 or F by 2R, because gamma is equal to 1 plus 2 by F. Right, this equation is clear, no? So this will become R upon 1.5 minus 1 or 2R. So this is a type of gas where Cv's value is 2R. Or degrees of freedom would be 4. Yeah. So now we want to increase the temperature of 10 moles by 30 degrees C. So delta U will be NF by 2R delta T. Oh, that's the same thing as NCV delta T. So 10 moles by 30 degrees C. So this should be 600 R or 600 into 8.314. So answers are given in terms of R. So it should be D. Answer is given as something else, is it?
Yes, sir. Answer is given to me.
Okay. Just make a correction in the answer key then. This should be the case. Okay. Moving on to some questions from exercise 1. Question number 8 and 16. Okay. Let's try and finish these. Okay, let's start with this question. This is from exercise 1 of Heat and Thermodynamics. So it says that coefficient of apparent expansion of a liquid in a copper vessel is C and in a silver vessel is S. So if the coefficient of volume expansion of copper is gamma C, what is the coefficient of volume expansion of silver? Okay. So basically, you know that if a liquid has coefficient of volume expansion of, let us say, some gamma, okay, and it is in a vessel which has coefficient of volume expansion of gamma 1, then apparent coefficient of volume expansion, that becomes how much? It becomes gamma minus gamma 1, right? This is pretty easy to understand. You see what is happening. The vessel was calibrated correctly at some volume. So the least count of the vessel is correct at T equal to T naught. Okay. And suppose it measures the volume V naught at T equal to T naught. So at the new temperature, T naught plus delta T, the true volume, say V, will be V naught 1 plus gamma of the liquid into delta T. Okay, because you've taken gamma of the liquid as gamma. But the least count of the measuring device, that will become whatever unit. Okay. So here the least count was equal to 1 unit of volume, because at this much, okay, but that will become 1 unit into 1 plus gamma of the liquid. So that's gamma 1, sorry, gamma of the container of the vessel into delta T. Okay. So the measured volume, that will become the true volume divided by the least count. Na? So it will become V naught 1 plus gamma delta T upon whatever unit of volume we are using into 1 plus gamma 1 delta T. So this will become V naught into 1 plus gamma delta T into 1 plus gamma 1 delta T to the power minus 1. So we approximate that and open the bracket and all that. So this becomes approximately 1 plus gamma minus gamma 1 delta T. So this is clear now? So this is the measured volume. So the measured volume will be the apparent coefficient of volume expansion based. The apparent coefficient of volume expansion becomes the coefficient of volume expansion of the liquid minus the coefficient of volume expansion of the container. Okay, so hope this relation is clear, Nikita?
Yes, sir.
Okay. So now based on this, now you can see that if the liquid has the coefficient of volume expansion gamma, copper has this kind of volume expansion and silver has this kind of volume expansion, then the apparent coefficient of expansion in the copper vessel will be gamma minus gamma C, and the apparent expansion in the silver vessel S given to us will be gamma minus gamma of silver. So from these two now we have to find out this thing. We have to find out this because we are given this. So we have to eliminate gamma. So you can just subtract the two equations. Got it? Now this is clear?
Yes, sir.
Okay. Only thing is, I think one of them is you have to calculate the coefficient of linear expansion. So finally, you have to divide the gamma of silver by 3, because you have to find out the coefficient of linear expansion. Okay, let's try to fit in at least another question. Okay, let's come to this one. Question number 8 of the same exercise 1. Just putting it up on the board. Okay, Okay, so we have here solid sphere of radius r made of bulk modulus. Now just leave out the question related to bulk modulus. Okay, we will read about this later. Bulk modulus of elasticity is basically the change in pressure upon the fractional change in volume. Okay, but for right now you leave out this. Okay, you leave this out. This is to do with elasticity chapter. Okay, so any question where you see the word modulus of elasticity, whether it is Young's modulus of elasticity or Bulk's modulus or coefficient of rigidity or whatever, you leave these questions out for the moment. When we do properties of matter, we will discuss it then. Okay.
Okay, sir.
Okay, so we will, okay, let's see one more question. Let's try to finish this one also. So 12th question. Coefficient of thermal expansion of steel and a metal X are given. Okay. So alpha of steel, alpha of the metal X. They are given as 12 into 10 raised to minus 6 and 2 into 10 raised to minus 6. Now at 40 degrees C, the side of a cube of metal X was measured using a vernier caliper. The reading was 100 millimeters. Okay. So the side of metal X was measured to be 100 millimeter at 40 degrees C. Okay. If you used a vernier caliper, then you would probably measure it as 100.0 millimeters. Because the least count of a typical vernier caliper is 0.1 millimeters. Okay. Okay, anyway, so assuming that the calibration was done at 0 degrees C, then the actual length of the scale was how much? Okay. So see, the thing is that at 0 degrees C, the vernier calipers, this thing, least count would have been 0.1 millimeters. Okay. So at 40 degrees C, the vernier caliper's least count has become something false. It has become 0.1 into 1 plus alpha of steel into 40. Getting the point of it? Okay. Now also, let us say that that particular cube, its side length at 0 was something. So its side length at 40, the actual side length at 40 would have been L0 into 1 plus alpha of x into 40. Right? So these two are clear now. Okay. Now at 40 degrees C, the measured value is this. This is the measurement. Okay. So measured value क्या होता है? It is the true value divided by the least count. So at 40 degrees C, the measured value of L is actually L's true value divided by the least counts, which is a false value over here. So the true value is L naught 1 plus alpha of metal X into 40. But the least count is 0.1 mm into 1 plus alpha of this thing, steel into 40. And this is actually how much? It is 100.0 millimeters. So from this, we have to find out L naught. So L naught you can see is 100 millimeters into 1 plus alpha of steel into 40 upon 1 plus alpha of x into 40. Okay. So now just bring this to the numerator and fixing it. So it will become 100 into 1 plus alpha of steel minus alpha of x into 40. Okay, so just calculate this value, you will get the answer. Is it clear, Nikita?
Yes, sir.
Okay. So now just put these values here and calculate it. Okay. You get the answer in millimeters. That is the true length at 0 degrees. Okay, so people will conclude here today, and just you have sent me some doubts from HC Verma and all also, some of you. So just send me that once on WhatsApp also. So I'll try to give you some hints. Otherwise, next time we have a doubt session, we will discuss the HC Verma doubts together in that. Okay.